Howdy everybody, I hope you guys are doing great. Howdy everybody, I hope you guys are doing great. So right now, today, on this wonderful day, I just decided that I want to make a video. And I want to make a video explaining step functions because I need to get caught up in diffie-q. And basically, I think this could be very helpful for me to kind of get some input and to like display my knowledge a little bit and try to see if I can refine it. So I'm gonna post this video. It's gonna have two examples on evaluating step functions and stuff, and I'm also gonna give a brief rundown on how exactly everything works with a step function. And if you guys have any input or you guys want to leave comments on this video, please do. If I can make any clarifications, that'd be awesome. I'm also going to be deriving the Laplace transform of a step function. All right, so first off, what is a step function? So what is it? Well, a step function, that's kind of a weird question mark. A step function is literally just a different way of representing a piecewise function. So for instance, let's just make a graph. We can kind of represent a step function here. This is a little thick. Yeah, I think I actually like this thickness better. I don't know why. So we're gonna define a step function. So a step function is literally just another way of writing a piecewise. So you have your t, you'll have your y or x or whatever variable you really choose. And then you're going to have like a straight line until you get to the point you want to be at. And at that point, there's a discontinuity. So this will be at c. And at this discontinuity, your function will immediately jump to a value of 1. So it's a step function that basically takes that basically is 0 until it reaches c, in which case it becomes 1. So it's 0 if t is less than c, and it's 1 if t is greater than c. So that's cool. So this is a step function, and this is the notation that it uses. So this notation just means like u for unit. I don't know what it actually means. U for the step function, c is where you do the jump, and t is your independent variable. So we're going to just write that independent, and this will be jump, jump point. Because technically the function exists at both the left and the right. But the limit as a function approaches c does not exist, which is interesting. All right, so that's basically a quick definition of a step function. Now, I want to do something that I've wanted to do for a long time in math. I'm going to represent the absolute value of x as a function that's not a piecewise using Heaviside functions. So first off, let's graph it real quick. Everybody knows the graph for the absolute value of x. It's very, very famous, very popular. I had to take the derivative of it and all that. And it's basically this. It's just a piecewise where it breaks into negative x when you're less than 0 and positive x when you're greater than 0. So the stepwise function looks like this. Very, very famous. So yeah, this is basically the piecewise, and representing it with Heaviside functions is very straightforward. So you can have the absolute value of x equals negative x times 1 minus u naught of x. And then this will be plus x times u naught of x. So basically this part corresponds with this part of our piecewise, and this part over here corresponds with this part of the piecewise. And it makes sense because, you know, this value has a value of 1 at 0, and this value is 1. So as soon as it passes 0, this part will basically cancel, and you don't really care about negative x anymore. And this part will prevail, because if it's before 0, this value is to 0, and when it's after 0, it has a value. So yeah, that's the absolute value of x represented with Heaviside functions. And this is something very cool that I've wanted to do for a long time in math, and I just learned how to do it just a couple weeks ago. So yeah, that's awesome. Now what we're going to do is we're going to try and evaluate the Laplace transform. So we're going to evaluate the Laplace transform, or like rederive it. So we're going to rederive it. It's been derived many times in the past, and this will be another time in which it's derived. So that way you and I can actually see where it comes from, where it emerges. So first of all, we want to define it in a way that's useful to us. So we're going to define our useful function as being uc of t times f of t minus c. And all this is it's shifting your f of t by c. So you shift it to the right of c. So if you have like some, I don't know, you have like a sine function. If you have a c here and you want to start your sine, or you want to start your function from here rather than starting at like the middle, like if it actually goes like this, right? You don't want it to start from up here and continue. You want it to start from the beginning. You want it to start from its initial value. So yeah, that's what the shift is for. And then the uc of t is basically our step function that turns this function on. So it turns it on. So this is like the on switch. So it turns it on at c. So yeah, we already established this, just recapping it. Last time I'll do that. All right, so now we're going to plug it into our wonderful Laplace transform integral. And as we know, the Laplace transform, and we'll just call this f of t, yes? Or actually, no, we'll call it g of t. So our Laplace transform of g of t in the S world. Sorry, I'm going to get water and I'll be right back. All right, it's very well known to be the integral from 0 to infinity of uc of t f of t minus c dt. All right, so this is pretty cool. Now what we want to do is we kind of want to do a little bit of change of variables here, because this is like hard to evaluate, and we don't really want to integrate the step function. We want to avoid as much of that as possible. So what we're going to do is we're going to do a little bit of a change of variables. So this t minus c, we're going to end up equaling that to, I don't know, let's just say z. So now t minus c will equal z. Well, what happens then? This integral, so we're going to do change of variables, cv. Erase this little dot over here. It ends up being the integral of c to infinity of f of z. Oh, I forgot something very important. I'm going a little fast here, so I did forget this, and it's an honest mistake, but it wouldn't be a Laplace transform without the e to the negative st. Very fundamental. You know, I am new to this, so I do make mistakes. So of course, you do not want to forget that. Very critical, very critical. So now we're going to do our change of variables. F of z, we're integrating from c to infinity, so the function only exists after c, which is pretty important. Actually, I missed a middle step. Let's rewrite it as c to infinity of f of t minus c e to the negative st dt. This is equivalent to that. You can see it right away. Sorry, I should have written the middle step earlier, because now when we do a change of variables, the c will go back to 0. And the reason for that, you'll see in a second. So we'll go from 0 to infinity of f of z, and negative st, well, if this is t minus c, and we're changing it with z, well, t equals z plus c. Just rearrange it. You can see it very clearly. So we're just going to replace the t with z plus c dt. Alrighty. Let me make sure everything is on track. Yes. So also, why does the integral change from c to infinity to 0 to infinity? Well, the value c, if you plug it in for t, what happens to z? So if you sub in c here, you end up with c minus c equals z, which also equals 0 by definition. So now, if we're integrating from c, c will become our new base value, which ends up being 0. So it's kind of funny, right? This is also why I skipped it earlier, is because like you basically get rid of the Heaviside function and then get rid of it again. So it almost becomes like a non-issue in a strange way. All right. So now we have our new value, our new integral, sorry, and we want to, do a little more rewriting. So right now, what you notice, I actually made an error here as well. This is dz, not dd. I'm going past, I make errors, I'm sorry. All right, dz here. Now, with this dz, we can split that e into two parts. So we can have our f of z, and then we'll do e to the negative sz times e to the negative zc dz. Or sorry, sc dz. Now, what do you notice about this e value? This e value here is not dependent on z, so it's independent of z, which means we can take it out of the integral. So we're going to go ahead and do that. So we'll have e to the negative sc times the integral of 0 to infinity of f of z e to the minus sz dz. Now, what is this? We basically remade our little Laplace transform again. So we're going to treat this as the Laplace transform of f of s. So this is equal to the Laplace transform of, what was it that we defined earlier? G of t, right? G of t. So the Laplace transform of g of t will always be this, where f of s is the value outside of the Heaviside, is our f of t minus c, but shifted back. And then the Heaviside function basically gets turned into this e to the negative sc. So this is a very important general form that we could use. So yeah, sorry about all the mistakes earlier. I swear I'm more thorough, but I just feel like being speedy now because I want to get through this so we can focus on the actual fun part, which is the problems. So we're going to go find a new place in our little universe that we have, and we're going to say problem number 1. So our interesting problem is not going to be an initial value problem. It's not going to be anything like that. It's just going to be rewriting a function as a step function. So we're not going to use the Laplace transform we just derived, but we're going to become a little more familiar with step functions themselves by writing this function, t to the 4 plus 3 sine, let me write this more near for you guys, plus 3 sine of t over 10 minus 1/2. And this is going to be true when t is less than 5, and this is going to be true when t is greater than or equal to 5. So we have this piecewise function, but we can't really manipulate it in any meaningful way. If we do, we're going to have to do these 2 branches, which is very tedious. Instead, we can just represent it as one function, because why not? So we're going to rewrite it. So we'll have our f of t is now going to be equal to t to the 4, because what you notice is t to the 4 is true regardless of what side of f of t you're on, plus u sub 5t, because this only activates at the 5 point, so you want that 5 to be your c value, and you basically just multiply by the thing you want to turn on at that point. And yeah, t over 10 minus 1/2. Now, so we have a function, and so yeah, we basically converted it from a piecewise to something linear, as one, not linear, sorry, but as one function. Now, we want to take the Laplace transform, so we're going to do that, because why not? We might as well, right? So we'll do the Laplace transform of f of t is equal to the Laplace transform of all this stuff. Well, we can write it out as each chunk discretely, and we can evaluate it from there using linearity. U to the 5 t times 3 sine, and we're going to try and factor out the 110 here. So we're going to do 110 times t minus 5. And the reason why we do that is because we really want the shift in here. We really want the shift in here to be equal to 5 step units. Because remember, we want the function to be in the middle. I think I deleted my doodle. Sorry, I've been having some weird sickness recently. My throats have been acting up. All right. So now we have this Laplace transform. Well, we can basically just use our lookup table. So if you're in a differential equations class, you'll likely get a lookup table, which means that you're basically going to be able to take the Laplace transform for things in specific forms without needing to rederive it with the integral every time. So we're going to try and take you probably already know that because this is like very midway into the process of taking a differential equations course. They rarely teach this at the beginning. So we're going to use our derivation that we made over here. So the derivation we made is e to the negative sc f of s. Well, s here is 5, so e to the negative 5s times the Laplace transform of this wonderful thing. So the Laplace transform of sine of 1/10 ends up being 1 over 10 times 1 over s squared plus 1/10 squared. So boom, you took the Laplace transform of our first ever piecewise function. So that's pretty cool. All right, now what we're going to want to do is we're going to want to solve an IVP. So we're going to solve our IVP, and that'll be the last thing we do tonight. So yeah, this is probably what a lot of you have been waiting for, because this is the actual useful part of it. This is where it becomes applicable to engineering, to science, to whatever you're studying this for. We're going to solve this IVP. Y double prime plus 3y prime plus 2y equals g of t. And we also have the initial conditions. Y0 equals 0 and y prime of 0 equals -2. So you can probably already see that this is going to be kind of a nightmare. Because g of t is not a normal g of t, it's a piecewise. So we're going to write it as a piecewise, and we'll convert it to its Heaviside form, and then we'll do a bunch of fun stuff, which is going to be lovely. So this is the definition of g of t. So you have 2, you have t, you have 4, and it's going to be lovely because you all love learning, right? I assume so. Otherwise, you probably would not be watching this video. It'd be weird for somebody to watch this and not enjoy it. That'd be like kind of analogous to torture. So yeah, if you're doing that, I would highly recommend seeking some help or something. All right. Anyways, so we have 2t4. And now we can write our new function. Or we can redefine g of t using the Heaviside function that we worked so hard to understand up until this point. So we can kind of rewrite it as 2 times 1 minus u sub 6 of t. So this is just this, remember. Everything that's to the left of u sub 6, in this case, ends up being 0. So it only exists to the right of it. Or it only exists to the left of it, sorry. Plus t times u sub 6 t minus u sub 10 t. Interesting how we did that. Let me just rewrite it in a way that's a little more clear. u sub 6t minus u sub 10t. All right. So this is basically saying if it's between 6 and 10, because if it's after 10, then this guy evaluates to 1, this guy evaluates to 1, it cancels to 0. If it's after 6, this guy evaluates to 1, but this guy evaluates to 0, so it remains as 1. So this is basically, oh yeah, the window between 6 and 10, so it perfectly details this part where t exists. Now we want the part where 4 exists, which is just 4 times u sub 10 of t. It just exists after the t value 10. All right, so this beautiful thing is our g of t, which is just wonderful, isn't it? Now what we're going to do is we're basically just going to rewrite it. So we're going to factor all the things together, and we're going to try and make it a little cleaner. So we're going to write it as 2, because you can distribute this 2, minus 2 plus t u sub 10 of t plus 4 minus t u sub 10 of t. And this u sub 10 is not supposed to be a u sub 10, it's supposed to be a u sub 6. Very sorry about that. So now we have it written where all the terms are kind of gathered together, and you can kind of see immediately how this comes about. You got your 2 here, and you also got your t here, and then in this case you have your 4 here, and then you also have your negative t here. So it comes together quite nicely, but now we want to put it into a way that's Laplaceable. So it's Laplaceable. So we're going to make it Laplaceable. And how we're going to do that is we're basically going to do the wonderful, magical thing of adding 0. So we're going to have 2 minus t minus 6 plus 4. Now, it's like, why would you do that? This is equivalent to that. Why would you just do 2 minus 6 plus 4 if you could just write negative 2 minus t? Well, oops. Interesting. Should be the other way around. Because this will evaluate to negative 2. Negative 2. All right, well, I guess we'll faffle. So we'll flip these sides around. So it's like, why would you actually, we're not going to flip the sides around. Because it is a negative 2. This also has to be a negative t. Which is strange. U sub 6 of t. Oh, that's why. I'm being dumb. This is not a positive 2 at all. It's a negative 2 to begin with, because 2 times negative u sub 6 of t is just negative. We'll rewrite it in here. Sorry, I omitted this earlier. Errors cascade like that, so you need to catch them while they're young. All right, so why are you writing it like this if it's essentially the same as that? Well, remember, we want the c to be over here in this minus state because we want the shift to align with it. So that's why we're basically adding 0. All right, and we'll do the same thing over here. We'll end up with interesting. Just deciphering my notes a little bit. Sorry, guys. Well, we know that we're gonna want a t minus 10, right? And we know that this is gonna end up being a minus. And if we have a minus 10 in here and a positive 4 there, this is basically a negative 4 inside, so we're gonna want to add 6. Add 6 u sub 10 of t. Because if you do negative 10 plus 6, that's a negative 4. Distribute the negative, you'll have the negative inside. So yeah, this is basically equivalent. Now we're going to want to take the Laplace transform. We're a little lost in the weeds now, but you have to remember, we're trying to solve this differential equation here. Sorry, this highlight should be a little thicker. There we go. So we're trying to solve this, and this has a left-hand side and a right-hand side. So we're going to solve the right-hand side first, which is this stuff. We're going to take the Laplace transform of the right-hand side. Take Laplace transform of RHS. So the Laplace transform of y double prime plus 3y prime plus 2y is something you do with the lookup table, and you know that this is s squared f of s minus s of f0 minus f prime of 0 plus 3 times s f of s minus f of 0 plus 2 f of s. All right. So this is, let's see how this connects here. So I'm just gonna like bring down a copy of it so you can see it nice and clear. So this part here is y double prime. This part here is 3y prime. And this part here is 2y. All right, so that was the easy part. Actually, we're not completely done yet. We're going to want to condense it a little bit. So we're going to rewrite it. Rewrite by condensing it. Rewrite it as s squared f of s, and we're rewriting it, but we're also applying initial conditions. Apply ICs. Because if you remember, we had these initial conditions that we defined as earlier, and I'm using f's now. I realize that, and these are y's, but just know that they're identical. So we're going to apply our initial conditions. We're going to copy this and bring it down. And we'll bring it down, and we'll see that we still have our s squared f of s. And now we do plus 2, because f of 0, that's just 0, so this guy will cancel. Different color probably, 0. And we see that over here we have another f of 0, so this guy will cancel too. So those two will end up being 0. Negative, f negative over negative is a positive, so we'll end up with plus 2. And then we have plus 3 f of s, or s f of s, sorry. 3s f of s, and that's from this guy here. And then we have 2 f of s. Right? So we have this guy here, then we have our 2, which comes from this initial condition, and then we have 3 f of s, which comes from here, and we have 2 f of s, which comes from there. Very simple, very straightforward. Now what we're going to do is we're just going to rewrite it in a more condensed form again, and we're going to like try to isolate it. I'm going to try and isolate our Laplace transform of the function. So basically we'll get f of s times s squared plus 3s plus 2, and then all of this is plus 2. So yeah, you should be able to see very clearly how this comes from here. And so this is the Laplace transform of the right side. So that's an ugly shape, oh my gosh. So this is the Laplace transform of the right side. RHS Laplace transform. All right, So now we need to do the wonderful, wonderful part of doing the left-hand side. Or, did I call it the RHS the whole time? This is clearly the left-hand side. We defined it as that. This is the left-hand side. So have I been calling it the right-hand side? I've been writing it as the right-hand side. I think I've been saying left-hand side. It's late. I'm sorry, guys. I mean RHS. So we have this Laplace transform of our right-hand side, and now we need to move over to the left-hand side. The left-hand side is way more annoying, because now we have to deal with a bunch of weird things. So if you remember, we defined our left-hand side to be this. This is our left-hand side. I just kind of boxed it for you. I'm actually going to copy it and bring it down so you can manipulate it a little bit. So we'll have it here. And just to remind you all, this is g of t. And you want to take the Laplace transform of it. So, yeah. Laplace transform individually, because I wanted to focus more on the partial fraction decomposition side of things. So this particular problem, this exact problem actually, was taken from Lamar's online notes. It's actually Paul's online notes, and he's from Lamar University. So it's very reputable, very useful source of information. So you can find the proper derivation of f of s. But you remember here, like, oh yeah, your f of s times s squared plus 3s plus 2 equals your g of t. Well, I mean, you could just also Laplace transform your g of t and divide it. So if you do that, you're just going to have to trust my word on this. If you want to see the entire derivation, you can definitely see it. You just need to go to the resource that I'm using, and you can see it more thoroughly, because I want to focus more on partial fraction decomposition. And I would do this, but this video is long enough. I kind of got to keep it a little shorter. So just kind of take my word on this. If you want to isolate f of s here, what do? Well, you just divide this thing by that. You just divide this by that. So that's exactly what we're doing. So f of s equals 2 plus 4e to the negative 6s minus 6e to the negative 10s over s times s plus 1 times s plus 2. I'm gonna bring it over a little bit. Ooh. Whoa, that's weird. Oh, geez. I hate Microsoft thing. All right. And then we're going to add e to the minus 6s minus e to the minus 10s over s squared times s plus 1 times s plus 2. And then we're also going to subtract 2 over s plus 1 times s plus 2. This derivation, you could definitely get it yourself. It's just a little tedious, and the partial fraction decomposition is tedious enough. So I'm just going to keep my work there. Now, speaking of that, what we're going to do is we're going to use a very useful trick. We're just going to define q of s to be equal to 1 over s times s plus 1 times s plus 2. And if you look, that's literally this. So if you were to multiply this thing by q of s out here, right, you would get the same thing, basically, is the idea. So we're just going to get q of s, and we're going to split it up into its fractions, and we'll multiply this numerator later on by this new q of s that we derive. So yeah, we'll just say this is equal to a over s plus b over s plus 1 plus c over s plus 2. Very classic process. And here, what we're going to do is we're basically going to divide everything. So you end up with just 1 equals a times s plus 1 times s plus 2 plus b times s times s plus 2 plus c times s plus 1. Now you have all 3 distinct s's that you're going to do. So first off, we're just going to select s as 0, and we're going to change the color here. We're going to select s equals 0. When s equals 0, this guy cancels, so you're just left with a, and you end up with 1 equals 2a, which means that a equals 1/2. Wow, so magical, so cool. So a equals 1/2. All right, and now we're going to select our next s, which will be s equals 2. All right, when s equals 2, this guy can't, or -2, sorry. Negative 2. When s equals -2, this guy cancels, that guy's the only guy that's left. And so you basically just end up with -2. -2 plus 1 is -1. -2 times -1 is 2, so you get 2c is equal to 1. Which means that c is also equal to 1/2. Just like a is. Very cool, very nice. All right, and now for our final s, we'll select s equals -1, and this should be the easiest one. Plug in -1, this guy cancels, all that's left is here. -1 times 1 is just -1, so negative b equals 1, which means that b equals -1. Wonderful. So now we have all our values, and we can break q of s down into 3 discrete pieces. That's a lot easier to take the inverse Laplace transform for when we get our final answer. All right, so we have our 3 pieces. And now we're just going to rewrite q of s right now. So you have a good idea, or not a good idea, you just have the answer to what q of s is at that point. So 1 over 2s minus 1 over s plus 1 plus 1 over 2s plus 2. And you see where this comes from very clearly, because you just, plug in your variables for this value, these fractions up here that we got earlier. All right, so this is q of s. We're going to box this, and we're going to keep it in our back pocket for later. If I can draw a box, sorry guys, box it. Boom. Perfect. Wonderful. Primo. All right, so we got our q of s out of the way, which is this function. Now we're going to go ahead and we're going to move on to our g of s. So we're just going to define g of s. I know I used g of s earlier, but I decided to abandon that pursuit of finding the inverse transform, or not the inverse transform, but just the transform. Like I said, exercise for you guys. I'm not going to harp on it anymore. We're just going to write it out here. 1 over s squared times s plus 1. Also, another thing I noticed about diffie-q is like everything is really hard to keep in one spot. Like there's so much sprawl when it comes to differentials. Like differentials I just noticed are like messier than integrals, because the integrals generally, if you integrate like a term like a, you'll get to v, you'll get to x position, and like it kind of truncates a little bit, I think, especially if it's over a region, because you can integrate over a region, right? And like if you do that, it's going to be a number. Whatever you put in here, if it's t related, is going to be a number. Actually, anything you put in there that's a real value, that integral is just going to be a number. But if you take a derivative of just some function, not the integral, this is a mess. It's just another function. So differentials tend to be very messy by nature. Anyways, that's a side tangent. So this is, we'll just rewrite it in its partial fraction form, blah, blah, blah. you break up the denominator into 3 parts, and you're able to evaluate it that way. And then we're just going to rewrite it as 1 equals s plus 1 times s plus 2 times a plus s. This is an ugly plus sign. I hate it. Get rid of that guy. S squared times s plus 2b plus s squared times s plus 1 c. All right, now what s's are we going to select this time? So we're going to do the obvious choice again, and we're going to select s is equal to 0, and I'm going to choose this red color now. Select s equal to 0. When you select s is equal to 0, this guy cancels, this guy cancels, you're just left with a, so you end up with 1 times 2, that's 2a equals 1. Oop, what do we notice? Or sorry, 2, this is 0 plus 1. Interesting. How did I get through here? I think I did it wrong. I think it's supposed to be 1/2. Anyways, sorry for that. All right, now we're going to select s equals to -1. If we select s equals to -1, this guy cancels, this guy cancels, so you just end up with b. You end up with 1 equals 1, b, so you just get b equals 1. Not a lot more work to be done there. All right, and now we're going to select s equals -2. And if s equals -2, what happens? Well, cancel, cancel, blah, blah. -2 times 1 is -1. -2 squared is 4. 4 times -1 is -4, so -4c equals 1. Which means that c equals -1/4. Very cool. All right, so now we have our glorious g of s. And now we only have one more left to do, which is this guy over here, which we will call h of s. We'll go ahead and do h of s. And we're almost to the finish line. You guys have a lot of endurance for staying this far. So we're going to go ahead and rewrite g of s now with our new values. Just for completeness sake, so you have g of s is equal to 1 over 3s squared plus 1 over s plus 1 plus, or minus, my bad, I forgot it's a minus 1/4, minus 1 over 4 times s plus 2. Alrighty, so this is our g of s. This is another part of the puzzle. Now, finally, we're going to need to evaluate h of s that I called it. Okay, so h of s. This one's a shorter one, so it's 2 over s plus 1 times s plus 2, right? And it's going to be equal to a over s plus 1 plus b over s plus 2. We're going to move this guy over here a little bit, and move this guy to the left. All right, so 2 equals s plus 2 times a plus s plus 1 times b. There are two obvious selects here, so we're going to select s equals -1 first, and select s equals -1 first. Or, sorry, it's just comma. It's 2 equals a, not much more there, just that. And then we will select s equals -2. So as equals -2, this value is 0. -2 plus 1 is -1, so you get b equals -2. Fairly straightforward. All right, so we have our values for a and b, and now we'll write h of s, cut it dry, equals 2 over s plus 1 minus 2 over s plus 2. So now we have all the pieces to the puzzle, and we can actually get our answer. After all this work, we have h of s, q of s, g of s, all to plug into f of s here. And these are like the stones to our infinity gauntlet, so to speak. So we're going to finally, I'm going to write this in purple because I want emphasis, and purple's cool, and also the color of Thanos. All right. So now we're going to rewrite f of s in terms of our new stones we derived for infinity gauntlet. So our infinity gauntlet, which is f of s is going to be equal to big Q of s times 2 plus 4e. It's Q of s here, and then it's multiplied by this whole thing. 2 plus 4e to the negative 6s minus 6e to the negative 10s. So this is your first term. And then plus g of s. And we're going to move this guy around a little bit. Oops. Unable to see changes. That's great. Move it over here. Times e to the negative 6s minus e to the negative 10s. And then minus h of s. All right. So now we do all this and we put it into pieces. So we're going to put it into pieces like even further. We're very close to the final answer. 4q of s plus g of s. I'm going to factor out all the e's. Minus e to the negative 10s times 6q of s plus g of s. And then minus h of s. And we factor out the e's because we want to write them as step functions. So our final f of t, final answer, after all that, is 2 lowercase q of t minus h of t plus u sub 6 times 4q of s plus, or lowercase q, sorry, q of t or q of t minus 6, because it's a heaviside function, plus g of t minus 6 minus u sub 10 of t, and then this is times t2, of 6 f of t minus 10, and then plus g of t plus g of t minus 10. All right, and this is our answer. This is our final result. It was kind of a monstrosity, and going through details and all that, it can be a little tedious, but this is the final result. And it might not be completely satisfying because we do not have all of our Laplace transforms, but if you look, all of these are kind of trivial to solve. Like, you can use the table on them. There's not much more there to be set, and that would just make the final equation so much more complicated. But this is the answer to the initial value problem, the very beginning goal of all this mess. And yeah, if you want to see the missing parts of my explanation, go to Paul's online notes and read there. But I basically really just wanted to make this video because I wanted to be able to basically explain to you guys the process and to kind of read it aloud to you, kind of like an audiobook. Maybe you could solve it along with me if you're interested in doing that, or if you wanted to hear explanations. Also, I will be active, so if you guys post questions or you have any sort of feedback in the comments, I will read that. And so yeah, so this is basically all that there is to do with step functions, and hopefully soon I can do something that's related in the future, which is Dirac-Delta functions, and make a video on that as well, because the Dirac-Delta function is also interesting and also has to do with impulse functions, all sorts of cool engineering stuff. But yeah, thank you all for listening. If you guys have any more input, if you guys have any more interest in anything else, please do let me know. And yeah, thank you guys. It was awesome.